So, how do we get an ETCS train ready to make a move? Well, we need to give it some data to tell it about its characteristics. Because trains vary a lot. They can accelerate at different rates, their brake systems vary, and the efficiency of those brakes varies a lot. So what needs to be entered or confirmed by the driver before a mission can start? Well, we need to know who the driver is, the level they want you to operate at, the identity of the journey the train is going to make, so the train running number, and data about the train systems. So before we look at it in detail, let's just see how quickly a typical driver can enter this information. So the driver identity is not actually used by the ETCS system. It's not reported to the Radio Block Center, the RBC. However, it is stored in the black box, known as the Juridical Recording Unit, or JRU. This can be useful if a railway undertaking is looking back at the driving behavior of an ETCS driver. When the system starts up, it normally knows the level that it was last operating in. However, if the train's position is now unknown or invalid, the driver will be asked to enter or confirm the level. There are also locations where more than one level may be applicable. In that case, the driver can use the menu system to change the level to the one they want to operate in. The train running number is entered as an 8-digit number. That is the standard format in Europe. However, in GB, we use a different format, an alphanumeric format. So there is an option within the ETCS system to enter the data as would be done for the GSMR voice radio system. That format is a number, a letter, and 2 more numbers, 1 alpha 2 3, for example. To make it unique, we normally add a 3-digit location code, often part of the signal or marker board number. The TRN, the train running number, is sent to the RBC as 8 digits, so our alphanumeric one is converted before it is transmitted. Train data can be entered in 2 ways, preferably to use pre-programmed data, and this applies to multiple units, fixed formation trains, and regular workings, where the data can be defined in advance. The driver selects from one of a number of presets. This might be for a 2-car train, 2 2s coupled together, 3 2s coupled together. The preset provides the ETCS onboard with all the necessary information about the train to calculate the safe supervision of that train. For trains which cannot use presets, the flexible train data method is available, typically for freight trains, but it could include heritage passenger trains or some rescue moves. Some of the fields may be pre-configured, but the driver is expected to enter information in all of the other fields. So what are those fields? Well, we start with the train category. This covers the type of train, the brake settings, and the Cant deficiency the train can operate at. There are 4 basic types of train: passenger, tilting passenger, freight with the brake setting set to passenger timings, and freight with the brake set to goods timings. For freight trains, if you apply the brakes quickly, the locomotive and first few wagons will start to brake. However, because of propagation time down the brake pipe, the other wagons will not be braking as quickly, and so they will all catch up and bash the buffers. To avoid this, the brakes on a freight train can be set to apply slowly, allowing the air in the brake pipe to propagate down the train. Only the relevant types would normally be displayed to the driver. The train length in meters is entered by the driver, or it may have been obtained from systems on the train. To avoid having stupid lengths entered, the system can be configured so that only values within a certain range can be entered. If you've been on a train which is going round a corner, you may have noticed that you sometimes feel that you are falling into the curve or being pushed out of the curve. If you're being pushed out of the curve, that means the train is not leaning over enough for equilibrium to be maintained, and that is known as a Cant deficiency. Different types of trains, based principally on their suspension systems and the center of gravity, can tolerate different Cant deficiencies, which are shown as millimeters between the two rails. For a passenger train, there are three options: Pass 1, Pass 2, and Pass 3, which represent 80, 130, and 150 millimeters of Cant deficiency. Tilting trains are obviously designed to be able to go around curves faster without the coffee spilling, and there are 7 options allowing up to 300 millimeters of Cant deficiency, which would be something that a Pendolino, for example, could operate at. For both the freight categories, the options are 1, 2, 3, and 4, representing 80 up to 150 millimeters of Cant deficiency. The loading gauge of the train can sometimes be used to determine whether it is compatible with a route. The TSIs define a number of loading gauges. However, all of those gauges are significantly bigger than those used on the GB railway, so the loading gauge is normally not used. The impact of the train on the track is a combination of the weight of each axle and the spacing of those axles. Some bridges are particularly susceptible to high impact loads, and so speed restrictions need to be applied. There are 13 defined axle load categories, starting at the least damaging and working up to the heaviest and most damaging. The exact order is not perfect, but it does allow a certain discrimination between the heaviest trains and the lightest. If you're in a locomotive, normally the axle load category of the locomotive itself will be displayed and any heavier or more damaging options. Lighter options couldn't be displayed because the locomotive is the heaviest item. To work out how quickly a train will stop when it is required to do so, you need to enter the brake percentage, and this configures the onboard braking model. The information is taken through what is called the conversion model, combined with the length of the train, brake setting, and the speed range to generate emergency and service brake rates. These numbers are then used to supervise how fast and where the train needs to start braking. Each train will have a maximum permitted speed. This is entered in multiples of 5 kilometers per hour. Depending on the wagons or coaches being pulled by the train will affect the maximum speed. So what's it all for? Well, it's there to allow the ETCS onboard to safely supervise changes in speed and stopping locations. The train data is particularly important for the safe management of a train movement.